Next, we have Dana Yoerger talking about the ImmuneSavant. Now, he'll explain to us what the heck that is.
All right, well, looking at the clock, I see I'm between everyone and coffee, so I know what that's, where that puts me. Talking about sampling, making observations and taking samples in the mesopelagic with this new platform that we're just starting to develop called the ImmuneSavant. And I'll be giving you some details. It's actually advanced a bit more beyond this conceptual drawing right here. The basic idea is it's a autonomous vehicle, a powered one, and it will have the ability to track targets in the midwater region down to about 1,000 meters using stereo cameras and also with a high-quality science camera to record the observations. So it will be actively controlled by the cameras and stereo processing and, of course, with appropriate lighting. Okay, I guess I don't need to dwell on this slide too much with this crowd, but certainly we know that the Twilight Zone, the mesopelagic, is we have a lot to learn, and we have some nice tools, but we certainly need to expand that toolbox if we want to understand a lot of these processes. And the added impetus is that industrial harvesting is probably just getting going, but could be very significant in the near future. Okay, so the ImmuneSavant will complement many of the existing platforms that we have. We wanted to build something, not something that sort of encompassed the functions of things that of capabilities that we already had, but a platform that would basically fill in the gaps. And those gaps are basically filled by a vehicle that can move very slowly under very fine control. It will have a variable buoyancy system and thrusters that will work together. And it will be able to investigate things like migrating zooplankton, descending aggregates. And then it turns out if you can do those things, in speaking with members of our team, it turns out that you could probably do some very creative work in various kinds of thin layers. And a more speculative example here would be tracking rising bubbles and determining their fate. Now, I should emphasize that in addition to making these visual observations, we'll be recording standard sensor suites, the obvious conductivity, temperature, oxygen. We can add to that list as needed. And the other card that the ImmuneSavant will have to play is that we'll also be equipped with a pump filter sampler. I'll talk about that, the super. Some of you may be familiar with that. So as we're watching targets and as we're measuring many of the conventional aspects of the environment, we'll also be able to take pump filter samplers either on a schedule or in response to what we measure. And then, of course, those filters will be returned to be analyzed geochemically and also, of course, for molecular analysis. Okay, our partners, Hui, obviously, and Bari, and you'll be hearing about some complementary work later today from Kakani. Stanford is involved in the using stereo cameras to actually guide the robot. They have a fair amount of experience working with Bari in that. And finally, Chip Breyer, he's at UT, University of Texas, Rio Grande Valley, and again, he's involved in the sampling. So the ImmuneSavant has a heritage, I guess you could say. We're drawing on a lot of our previous experience. At Bari, oops, sorry, I hit the wrong button. At Bari, they have a vehicle called the Long Range AUV. And in fact, we will be using much of the guts of the LRAUV to actually make the Mesobot to take care of its most basic vehicle control and sensor management functions. There's also a new AUV at Bari called the I2 map, which is used for mid-water transects. It has a very high-quality imaging suite and basically is able to take the place of their ROV for their routine transects. And we've been learning a lot of lessons about the video system. We won't have anything nearly as exotic as what's on the I2 map in terms of size and power, but there's a lot of valuable lessons we can draw from. My own experience is more in vehicles for examining the seafloor, and I had to remark that they don't get a lot of play in this community, but in fact we have this particular vehicle, Sentry, has about 450 dives mapping the seafloor with multi-beam sonar, side scan, bottom photography, and of course the conventional sensor suites that you would carry. I say combined with its predecessor, ABE, we're pushing 700 deployments. And then, of course, there's a strong heritage with remotely operated vehicles, both from our Bari partners and in our own HUI work. And specifically, Bari and Stanford researchers did a project about 10 years ago where they had their ROV automatically following midwater targets like jellyfish. And they have a nice set of publications on that. So that was sort of our proof that this was a reasonable thing. Now, again, I don't need to elaborate on this with this group, but I think that we fit into unraveling these kinds of puzzles in many, many important ways. And I'll talk a little bit about how I think that this platform complements the other platforms that we have for this kind of work. And of course, again, no need for me to dwell on this here, but we can actually drop this vehicle, oops, I keep hitting the wrong button, I'm sorry, into the deep scattering layer. We can follow targets within it, and we can, or we can do more general investigation if we see an interesting a region with the sonars on the vessel. We can drop the Mesobot into there and have it do very precise surveys within there, visually recording the animals that are present. So we see a lot of potential for complementing a lot of those existing capabilities that we have. Now, of course, we have a lot of tools now. Why do we need another tool? These are the kinds of things when we're proposing a program like this, you have to spend a lot of time on. We think that we're very complementary with these. Obviously, nets will always be a mainstay of this kind of work. Peter Wiebe's a member of our team, and of course, his work with the MACNES and other systems over the years is well known. There are any number of very, very capable imaging systems for plankton. Probably at least half a dozen of them, all with their strengths, different optical designs that provide fundamentally different capabilities. We would distinguish what we're doing from this in that these systems, almost without exception, can survey. They can be put on a mooring. They can put on a fast-moving ROV or AUV. They can be towed at high speed, but they can't stop. And they can't examine these targets and look at them up close the way people would do, for example, with an ROV, and monitor those phenomenon continuously for long periods of time. But unlike an ROV, this system won't be limited by a tether, and it'll have much more endurance. And so we think it's pretty complementary there. And again, oops, I'm having trouble with the button here. Again, if we look at Bioacoustics, of course, which is extremely capable tool, we think that the Mesobot would have a lot of application for dropping into these layers and helping us figure out what's there, both through the imaging capabilities and also through the sampling. So what would you do if you could have a dozen super samples and very detailed visual observations in the context of these acoustic observations? And of course, conventional and evolving capabilities, sediment traps, and all of the kind of rich variations on those themes that are being developed now. We see a complementary role for the Mesobot in that. Just a few details here. This is a bit. This was our early conceptual view. We've advanced quite a bit from there. But we have lights. We'll have a stereo pair of cameras, a science camera. From the stereo, we get the range and azimuth, essentially, of the particular target. And then we're recording in higher quality with this camera. I should mention that many missions will actually start with the Mesobot on a tether. We'll have probably a fiber optic connection to the surface. That will allow, within a much more limited depth range, but that will allow our investigators to choose a target, to lock onto it, and then we'll drop the tether and it will continue autonomously from there. So you can imagine a variety of interesting targets that we'll be able to track. Again, we'll have the super, and the goal will be, by using the thrusters and a variable buoyancy system together, not unlike the way platforms like the long-range AUV have successfully demonstrated, we'll be able to be hopefully almost Lagrangian, kind of like the targets that we're tracking. Okay, a brief example from the Bari Stanford work. They've shown repeatedly that they can recognize targets. We can track them continuously. This work has advanced quite a bit since these publications about a decade ago. And particular, the challenges are to make these algorithms more robust and more able to deal with very complex dynamic scenes. And of course, another challenge is the fact that most of your targets are changing in shape over time. That's another challenge on the processing end. And finally, after you've localized the targets, you've selected your target and you're tracking it and you're localizing it, you have to figure out what you actually do with that information, much in the manner that a skilled pilot of an ROV isn't simply holding it in the center of the screen. They're making complex decisions based on anticipating the movements of the animal, whatever. So that's part of what we're automating. And Oscar showed you the little kind of embedded supercomputer. We'll be using exactly that same module in the Mesobot. It's evolved a bit since the one that he showed you, and that's one of the waves that we're able to ride of evolving technology. Literally, for under 10 watts, you have a really phenomenal amount of computing power that you can put in the vehicle, and it runs all kinds of standard software libraries. So we see a lot of potential for being very productive on that. Another sort of cousin vehicle, this is actually, this is the Clio, built by Chip Breyer and Mike Jakuba in our lab. It's an autonomous profiler. It's basically a platform for carrying these pump filter samplers down to depths of 6,000 meters, and then it'll be able to profile all the way back up. And so the Super has evolved quite a bit from these images that I've shown here, and we're able to take advantage of that. We'll be having basically a much smaller version of this kind of Super built into the Mesobot, and of course a variety of filters can be selected depending on the problem. They run filters from about 0.2 microns up to maybe 100 microns, depending on what your target is. Another project that's feeding into this would be a project that Govindarajan and Pineda did here at Hui using a REMUS equipped with a super and going out and showing how you can do precisely targeted sampling. And in the end, you end up with the pump filter samples. You've measured a lot of the physical variables along a very controlled pathway, and then you bring those samples back and you can do molecular analysis and reveal a lot of details about who's actually living there. In this case, they were looking at barnacle larvae, but we think that basic concept will be extended. And in addition to that kind of more conventional molecular analysis, of course, the eDNA possibilities are extremely exciting. So I think a major theme that's evolving from our Mesobot work is the visual observations along with the insight that being gained from these samples. A couple of use cases, and again, Kakani will be talking about this a bit later today. Find a larvation, lock onto it with the cameras, drop the tether, and then follow that animal for, we would hope, for a day. Some of the big challenges here are going to be, of course, this is the house with the little animal, the small animal living inside. And are we going to be able to stay with the target when the animal abandons the house? That's going to be a challenging one. But certainly step one will be just to track a single house for as long as, and watch the animal build the house over time. Another case, this was actually kind of our first idea. The project really started on a challenge from Larry Maiden to follow a migrating animal like a salp. This will be down to a depth of about 1,000 meters. We'll actually acquire the animal near the surface with the Mesobot on a tether, decide that's the animal we want, and then it will track for hopefully up to a day. That's the goal. And if you can do that and you have a super on board, many of these tasks like having the vehicle acquire and then survey and sample phenomenon like nephloid layers is extremely attractive and we think very possible. Something a bit more aggressive would be tracking things like descending aggregates. We would be able to track them to depths of 1,000 meters. That's going to be quite a challenge. The target is going to be hard to track. And we're going to need a lot of endurance because, of course, the sinking speeds are quite slow. So we're going to need some, probably more than a day's endurance on the vehicle. So a lot of challenges there, but again, the payoff would be great. We could determine the true sinking speed, and we could actually watch these aggregates evolve with time. I don't need to walk through this list, but we have a large number of design challenges that we're tackling right now. Probably some of the most obvious ones are the avoidance, attraction, and interference. So we're doing a lot of work looking at all of the techniques that we might use, different kinds of lighting, cycling the lighting different ways. We have to minimize our acoustic noise. The thruster wash is a big problem. If the vehicle, when it thrusts, it disturbs the targets, that's a big problem. And we need to be concerned about things like electromagnetic disturbances, and we're very interested in the possible use of things like counter shading to make the vehicle less obtrusive. So we have any number of challenges here, and that's what we're engaged in right now. We've been through a nice series of possibilities of how we can lay out our thrusters and what the implications of these are on the maneuvering capability of the vehicle and how much we disturb the targets and the environment that they're living in. And this was our conceptual design as of a couple months ago. Again, drawing from ROV designs, conventional AUV designs, and you can see we've got the super here down below, main housings, cameras, lights, all those all important recovery aids. wouldn't be a very successful deployment if you couldn't find it at the end. So by no means, between us and Bari, we've got thousands of AUV dives, so you don't have to remind us to be really worried about things like that. Our schedule, we're doing the preliminary and final design this year. We have a simultaneous effort going continuously with Bari and Stanford to work on the tracking system. Next year, we'll be actually building the vehicle, and year 3 will be testing at the dock and at sea. And of course, our acknowledgements, both from Hui Resources started this project, and we recently got funded by NSF OTIC starting this year to actually design and build this vehicle. So with that, I'm probably going to let people get to their coffee. Thank you.